So we still have some other sample problem here, similar to the problem a while ago. So we have here a uh, prop beam again. We also have a prop beam here, but the load is just a concentrated load, 160 kilonewton, located at the midspan of the beam. So same as what we did before, applying the method of consistent deformation, you just have to choose for the corresponding redundants, AX, or I mean, you just have to choose a redundant for the unknown values here, unknown reactions, AX, MA, AY, as well as CY. So we have four unknowns here, but we only have three equations of equilibrium. So therefore, this is also a first degree indeterminate structure. So we have one unknown here that we cannot solve. So with that, we have to choose one redundant here. And again, you have to choose the redundant in such a way that the remaining uh, structure will still be stable aside from being determinate. But the determinate portion is already automatic. Okay, if you will remove the number of redundants equal to the degree of indeterminacy of the structure. So you can choose uh, to make either MA or CY as your redundant. So for this particular example, you can see here uh, the solution have chosen CY to be the redundant. So after removing CY from the original structure, which is this, the resulting structure will look something like this with no restraint at the end joint C. So since there is no restraint at end joint C, if you will apply a 160 kilonewton load at midspan, the cantilevered beam will deflect with a certain magnitude. So for this particular case, we already computed the magnitude of the deflection, which is equal to this, and this is the corresponding bending moment diagram of the primary beam. Take note, this is just the primary beam subjected to the subjected to the external loading. So you can easily compute for the corresponding reactions here, the vertical, horizontal, as well as the moment. So therefore, you can easily draw the bending moment diagram of this corresponding primary beam. Okay. So after removing the redundant, it's now time to return that redundant to this structure. So this is our redundant CY. So the redundant CY can be expressed in terms of a unit load times that unknown redundant force. Okay. So if we have applied the unknown redundant force CY, obviously the cantilevered beam will be deflecting upward with some magnitude of deflection. Okay. And then you can easily compute all of the reactions here in terms of the unit load. So this is actually a technique that you can adopt. You are just expressing the redundant force in terms of a unit load with a magnitude of equal to 1. Okay, so that you can still numerically compute for for the reactions here as well as the deflection. So this is just a technique, but all of the values that you are seeing here must be still multiplied by the value cy. Okay, because all of these values that you are seeing here, this 5 reaction, 5 kilonewton meter reaction, 1, and the deflection are just all expressed in terms of cy. Okay, as well as the bending moment diagram. So all of these are in terms of cy. Okay, so again, with respect to the concept of moment, I mean the method of consistent deformation or force method, the actual deflection, which is equal to 0, must be equal to the deflection of the primary beam, which is equal to negative 50, and the deflection of the beam subjected to the redundant force, which is just equal to uh, 1 times cy. Okay. So the only unknown here is just equal to is the only unknown here is just cy. So therefore, you can definitely solve for cy, which is equal to 50 kilonewton. So therefore, value of cy is equal to 50 kilonewton, as you can see here. Okay, so the unknown value there is just equal to 50 kilonewton. Okay, so after you have computed 50 kilonewton, you can readily solve the other reactions here. You'll just have to refer to the original given beam. Okay, just put there the corresponding value of Cy and then just compute for the values of the other unknowns AY, AX, and MA. So this will be the values. And you can also draw the bending moment diagram if it is required by the problem. Okay, so in this case, we have chosen Cy to be our redundant, but you can also choose MA to be your redundant, just like what is done here. So we have to remove MA here from the original structure because that will be our redundant. So the remaining structure will just be a simply supported beam because we only have AX and AY here remaining, just like in the case of a hinge support like this one. Okay, so the primary beam or the primary structure will look something like this. So this is the applied load, and you can easily solve for the corresponding reaction for this primary beam. Okay, and then if we will be returning MA, if we will be applying MA here, the beam will obviously bend in this way, as you can see the broken line. Okay, so the beam will be changing its angle. So and whenever you have chosen a moment as your redundant, it's not deflection that you have to compute, but the change in angle. Okay, uh, that is usually in tandem. So if the redundant is a force, you have to compute for the deflection. Okay, if the redundant is a moment, you have to express this in terms of change in angle or simply the slope. Okay, you have to remember this part here. So from the previous examples, we usually choose we usually choose a force to be our redundant. That's why we have computed deflections. But in this case wherein we have chosen MA as our redundant, it's not deflection that we have to compute, but the slope. So for the primary beam, we have seen that if the simply supported beam will be loaded by 160 kilonewton load, it will bend like this, like the broken line. And as you can see here at joint A, where we have removed the moment reaction, the beam actually had a slope of, let's call it theta AO. And then if we will be returning MA, which is expressed in terms of a unit load again, we can easily imagine that the elastic curve will look something like this with a slope or change in angle equal to this. Okay, so just like what we did before, you just have to compute for the sum of this change in angle or slope and this angle. And their sum, in equation form, their sum must be equal to the original slope at the same point A. So as you can see here at the original structure, the slope at point A is just equal to 0. Okay, simply because this is a fixed support, and we know that for a fixed support, the tangent at that point A is just a horizontal line. Therefore, the slope of the beam at that point will just be equal to 0 simply because the tangent is just a horizontal line. Horizontal line has a slope of 0 degrees. Okay, so therefore, the sum of this slope and this slope must be equal to 0. So that will be your working equation. So it will just be a systematic procedure to compute for data. You can use again unit load method or virtual work method. You can just use the formula for the computation of slope mm over ei dx from x1 to x2. Okay, you just have to determine the moment equation for the virtual load and for the real loads from the primary beam. Okay, so that is just a systematic procedure that you can practice at home. Okay, we have another example here. Uh, This is came from the book of Kasimali, but I'll just leave this as an exercise to you. You can just try to read this and study this. The case is almost similar to what we are discussing. It's just the given problem the given problem has no specific values or specific load or specific values of load. You can see here the load applied to the prop beam is just expressed in terms of a variable m. So the only problem on this question is the tedious effort of computation, because all of your computation here will just be composed of letters because we have no specific values of loads. Okay, but in any case, same concept will just be used. Okay, another problem here, almost similar to what we have computed a while ago. So you can just try to refer here. And we also have another problem here, which is composed of continuous beam. So again, you can choose redundant as long as the remaining structure will still be a determinate and stable structure. Okay, so I'll just leave this as an exercise.